we can start with the questions from the chat for the speakers of our talk session, and let the speakers to first answer those questions. Then we can go into more general discussions.
Yeah. If I can say, actually what I would like to give is not a question, but rather a remark or comment. Maybe I will do that after the questions, no? What do you think?
Yes, yes,
so.
Yes. So let us first let the speakers to answer those questions, and
Yeah.
then we can start the new questions.
Okay, keep in mind.
Yes. Okay, so the first question we have is from Thomas. The question is to Kenji about the anomaly, which usually has ambiguity. For example, the consistent and covariant anomalies, and so does the corresponding current. Is it correct to see that this ambiguity is behind the non-convariance of the current you have shown us? How do we know this is the physical current? So Kenji.
Yes. So I can answer this. The short answer is no. Actually, there is no ambiguity. Of course, the consistent anomaly and the covariant anomaly, they are different, but there is no ambiguity. And in the case of the QCD chiral anomaly, it is global symmetry, so it is covariant anomaly. Okay, that's it.
Okay, thanks, Kenji. Okay.
Okay. So the next one is also to Kenji.
Yes, next one and the third one. That is actually my fault of a wrong notation. I'm very sorry, but that the index mu should have been z. I imposed the rotation along the z direction. And so I was always talking about the current along the z direction, but I actually misplaced mu in the place of z. And so that was completely my fault. I'm very sorry for the confusing notation.
Okay. Okay, so Dennis, are you satisfied?
Well, yes, thanks.
Okay. So this is for the second and the third questions, right?
Yes, I think both are clear, excluding maybe the third, the contribution of the Church-Simons current is actually like a boundary term, and the value is influenced by what we set on the boundary, and how do we consider actually what boundaries to choose in order to make something more physical?
I see. Yeah, this is actually a very, very interesting question. And so this question is applied to not only the gravitational theory, but also electromagnetic theory, like the partial J5 given by FF dual. In that case, also the Chern-Simons current divergence appears. And so there's always ambiguity to identify the Chern-Simons current. And so in other words, people say that the Chern-Simons current is unphysical because it is not gauge invariant. But if you take the total derivative, then what you have is actually completely gauge invariant, which means that that current can be actually separated into the gauge invariant part and the gauge variant part. And such gauge variant, non-invariant part is actually divergence free. So by taking the divergence, so that term vanishes to make the divergence, the current, the Chern-Simons current, the gauge invariant. So this means that there's always such ambiguity. But this also means that by using such ambiguity, the Chern-Simons current could be defined in a gauge invariant way. That is actually the point to transmute such unphysical current into a physical current. So this actually idea is implicitly behind the idea of the chiral magnetic effect. So this is very interesting point.
Thanks.
Okay,
I actually,
so-
if I
Yeah,
can,
yeah.
I have some just related question concerning boundary conditions. In fact, solving the Dirac equations, there are unitary transformations like Foldy-Waldheisen transformation, and somehow say that they are useful to perform the classical, semi-classical limit. And what about boundary conditions? Do they generally depend on which representation, which unitary transformation are you using? Are there some just preferred representation, or it's completely independent of the particular unitary transformation?
I'm not sure what do you precisely mean by the unitary transformation. Is that a transformation in color space or?
No, I mean just the transformation. For example, Foldy-Waldheisen is the way to eliminate the minus component of Dirac field. So, and this is done to have a semi-classical limit of this equation. And we studied, in fact, this transformation for external gravitational field. The spectrum is independent of that because this is just the unitary transformation. But I wonder, maybe in some boundary conditions do depend on the transformation, and in this case, this can be studied.
Okay, now I understand. Now I understand. So this is another very interesting point, and this is also the, quite related to the definition of the Chern-Simons current, in the sense of the spin and orbital angular momentum decomposition. In fact, as you say, by doing such unitary transformation, the spinor structure could be simplified. That is usually the trick to go to the non-relativistic limit of a Dirac equation. And in such a way, actually, you have a chance to define conserved orbital angular momentum, even though in relativistic theory, the combination of spin and orbital angular momentum is the conserved quantity. And so there is actually such kind of a discussion in quantum optics. But what is interesting is that if you see the Chern-Simons current associated with electromagnetic field, actually what you find
By the way,
is,
if you want to share your screen, you can do that. If you think it's
no, well.
Then you should stop sharing yourself then probably. Okay.
yes, I can stop.
So may I continue?
Yeah, please continue. But I just mean if you want to share your screen to help to.
No. Just I'm describing. So anyways, the Chern-Simons current can be actually the spin component of the electromagnetic field. So actually, in such a way, so how to define the Chern-Simons current in the gauge invariant way has much to do with how to define spin component of the electromagnetic field. So this is very interesting. So this is actively studied field. So there is no, clear answer yet. But that is not my fault. But because this is very actively studied subject.
Well, thanks, Kenji. Actually, just as I said, we applied this unitary transformation of Foldy-Waldheisen type to arbitrary gravitational field. So we may look for this boundary condition in that case. Okay,
I
thanks.
see. Thank you.
Yeah, okay, so next question is from Dennis to May.
Yeah, okay. I can explain this figure, but should I
Yeah,
share
okay.
my figure?
Yes,
or
please.
Okay.
Well, I was a bit confused by one plot as a slide 25,
yeah, okay.
as mentioned.
This figure, right? So this part is actually cut in this region, this part. So I mean this right upper, okay, this right figure is from this part of this figure. So this is the Polyakov loop as a function of temperature, T a very large temperature. But this figure is actually here in this part. And this is actually a kind of first order phase transition corresponding to first order phase transition here. So for different,
sorry.
Yeah. So for different omega, so this is for small omega, and there is a jump. And then this describes the first order phase transition here. So this is corresponding to our phase diagram previously. Oh, okay, maybe here. Yeah, maybe, yeah, here. This one. So this is actually corresponding to this TC. So this jump here.
Thanks for clarification. It is actually discontinuity or abrupt jump. I was a bit confused that it looked like some hysteresis curve that have a slight multi-valued function for a short range of TC. It's actually a discontinuity.
Yeah, we should show the discontinuity, this jump,
okay.
And actually remove this kind of curve like this. Yeah, maybe we should remove this kind of curve.
And also I wanted to ask, what does the chemical potential in case of gluodynamics mean? If there are two flavors, I understand what is a baryonic chemical potential, but what does it mean in pure gluon theory?
Okay, this is actually like a probe. So we add this chemical potential. We introduce chemical potential by introducing this U1. This U1, how do you say? This F square. So this is corresponding to mu. At the high, it's a kind of probe mu, not really chemical potential. I mean, not like quark matter and gluon dynamics. So we don't have really baron number there. It's just a probe mu. So maybe, it's a kind of a little bit confusing. Yes, you are right.
Okay, thanks for clarification. It's parameter of the holographic model of the U1 gauge field.
Yes,
thanks.
Exactly. Okay, thank you.
Okay, let me see. Next question is from Matthias to May about the possible astrophysical consequences, differential rotations, whether there is a differential rotation.
Yeah, this actually, I'm not sure. Actually, Matthias actually added some comments.
Yes, exactly. Yeah.
Some result by himself, maybe. Yeah, okay.
Yeah, so maybe I can make it clearer. I can maybe share my screen just to tell you what I mean. I have posted in the chat a paper which we wrote in 2017 about the differential rotation profile inside a hypermassive neutron star. And so maybe you missed my talk or I was too fast. Probably I can just show this here. You can see it, yes?
Yes.
Yeah. It's the interior of a so-called hypermassive neutron star after the two neutron stars have merged, and we are now in a co-rotating frame. So usually the star rotates a lot, yeah. you will see several tracers, and this red line here is 3 times normal nuclear matter, and here's the density plotted. And just what I want to show you that after the merger, each tracer particles here could then undergo a confinement, a deconfinement and confinement. So I think this would be interesting. It depends a lot on the just rotation profiles inside the hypermassive neutron star. And here you see, for example, for different equation of state, the omega, the differential rotation. So the inner core, the high density inner core of the hypermassive neutron star is not so fast rotating, but then it increases rotation. And if in such a case here, probably a hadron core phase transition could occur. The different viscosities it could be interesting. So this was just to make it clearer what I wanted to say here. So what do you think? When one has such an object with a slowly rotating inner quark core, and then suddenly some cells go deconfinement and confinement again by the freeze out, probably, then the vector particles due to the magnetic fields could have some astrophysical consequences. What do you think about that?
Yeah, I think this would be very interesting, but I at the moment I don't have a very quick answer for that. But I think we can have a look.
Okay, thank you.
Okay, thank you.
What do you mean by differential rotation?
With differential rotation, I mean, so uniform rotation means inside the interior of the star is rotating with the same frequency as the middle and outside. But when you have differential rotation, the inner, so in respect to the neutron star merger remnant, then the inner core is not so fast rotating, but then you have a ring-like structure which rotates very fast, and this is about in the range of 1 to 2 times normal nuclear matter, where this omega maximum is. And this is quite independent on the equation of state.
So it's not vorticity, it's still the rotation with respect to the center of the system, of the whole system. I mean, it's not a local rotation, it's still a kind of global rotation with respect to the center of the whole system.
Yeah, so maybe I can share my screen again and show you probably this thing here. Here you see the temperature inside such a hypermassive neutron star, and here you see the omega, the rotation profile. I can turn on the video. This is now not in a co-rotating frame, and you see that the inner part here is not so fast rotating, which is this blue color here, but then you have this high temperature hotspots where this vortices occur. But after maybe 10 milliseconds, 15, 20 milliseconds, this omega and temperature hotspots smear out to ring-like structure, giving after 20 milliseconds such a situation where you have this highly rotating ring, and the inner core is not so fast rotating. But this simulation is done without a hadron quark phase transition.
I see. I think I understand your point. Thank you.
Okay.
So can I ask a question?
Oh, sure. Yes.
to that point by Matthias. So in that case, you need to have the share, and so you must have some friction between different domains, and so what is the mechanism to support such a differential rotation? Or it should be anyway weakened by the friction between them, right?
So yes, so I have to say in these simulations, we do not have included any viscosity, neither bulk nor shear viscosity. Yeah, and
okay,
yeah.
Okay, thank you very much. Okay, I understand. Thank you.
Okay, so let's continue. The next question is from Massimo to Kazuya. Why the transverse confinement as a boundary? A different possibility could be mass shading. And there is also a comment from Kenji. It's possible, but then even for the chiral fermion, chirality flip is introduced by the boundary. So a better choice depends on what your main interest is. And also another comment is from Maxim. Yes, the MIT boundary condition, for example, breaks the chirality explicitly due to the chirality flip. Yeah, so Maxim and Kazuya, would you like to continue the discussion?
Yeah, I mean, it's a very naive question, actually. It's the thing is that as far as I see, what is imposed is like a back model, like condition at the boundary, right? Because of the flux of current vanishes there, which is exactly what an MIT back model is done. And the thing is that, however, if I have in mind a simple system, but even highly rotating stars or any chunk of matter that highly rotates, typically it has a natural method to lose angular momentum, which is by shedding stuff. No, it's basically it radiates away somehow, and then it reduces angular momentum in order not to become superluminal. And this also happens because there's no in this system the energy barrier is not sufficient, no, to keep matter inside, which are in general nuclear reaction. In this case, it's of quark matter. It's not clear to me why this boundary condition should apply, in the sense that there's if the system loses matter is because it's highly rotating, the right condition should be or that the system size has become too large, and so there's a nucleation of or say breaking of the bubble of quark matter in other bubbles, or there should be some kind of shedding of at the boundary.
Maybe I can answer. Okay. Yeah.
Yes. Yeah, please go ahead.
Yeah, it's in fact in quantum field theory there is a problem in the sense that you don't need even matter. You can have, for example, just usual quantum field theory, and there are also virtual particles which can just travel from outside of the good region where you have a good causality, and they go outside far away to the end of universe and then come back if you don't put the boundary. And that will may give to many problems. So that's why you need to fix the boundary. So it will give, for example, negative population numbers in quantum, given statistical physics. And in quantum field theory, it will give just some negativity, or I don't know, some instability. People were talking about rotational Unruh effect in some specific sense, which didn't appear. And so one should always put the boundary if you consider field theory. That's very much important. Otherwise, it leads to instabilities and to nonsense results. That's, yeah. And I would like to make some comment because I think what we call fastly rotating plasma at mergers, as far as I see from the numbers, is just static picture from the point of view of QCD, because in heavy ion collisions, we're right now talking about a few MeV frequencies, and that corresponds to 10 to the power 21 hertz. And that's really highly rotating. In astrophysical context, we speak about gigahertz, it's just nothing. I mean, it's static picture for us. So I'm afraid unless we have some really, really small whirlpools, like in quark-gluon plasma, then we can treat this situation in static way from the point of view of quantum thermodynamics.
Yes, indeed. In heavy ion collisions, the angular velocity is speed of light at the distances of order of Compton wavelength. So it's definitely much larger than any macroscopic length, right? This is the point.
Yes. So,
okay, I understand. Yeah. So there won't be any astrophysical consequences in respect to this idea I had. Yes.
So it looks like no. At least large scale of kilometers, it's no. There'll be no consequences of rotation from the point of view of high energy. I mean, from the point of view of quantum thermodynamics. But if you have some small whirlpools, which are built in there of the order of a few Fermis or tens of Fermis, then they would emit some highly radiating particles with according to the astrophysical scale. But that you need really to have small whirlpools, not object of the size of 1 kilometer. It's for us, it's static.
But still, I mean, what is unclear to me is why one imposes a bag-like condition, right?
Because you don't want, for example, Kenji imposed different conditions. The general idea is just not to leave the particle go outside, physical degree of freedom, go outside the rotating region. Because what we consider uniform rotation. It means that end of universe is also rotating. It's not radially dependent. It's not kind of Rankine vortex. It's just a uniformly rotating thing. So you need to put some boundary to stop it. It's uniform.
But the thing is, I mean, if there's a boundary, that means that it's a potential barrier, right? Where does it come from?
No, you can first of all, okay, of course you can make physically, for example, in the confining regime, okay, if you have confinement, for example, in the MIT box, you know that fermions cannot go outside because of the bug, because outside you have confinement. So fermions don't exist as free particles there. That's why you can impose, say, in the model calculation, you can say, okay, Fermi mass infinite outside the bag. That's one thing. Another thing, just to say that you have the boundary condition, which is physically equivalent, which just reflects your fermion bag.
Right. I mean, the thing is, however, that the length scale of confinement has nothing to do with the length scale that you have from rotation.
Okay, that depends on the velocity of rotation of an omega. Length of confinement, 1 Fermi. And if you consider rotation, for example, of one, say, 200,
yeah, but
1 Fermi.
Yeah, but that comes back to my question. So the effect. So maybe I was not clear enough. So one thing is whether if your length scale of rotation, which comes from rotation, is shorter than the length scale of confinement, you should have string breaking, in my opinion.
Not string breaking. String would not form. String would not form because of asymptotic freedom.
Right. No. But the thing is that if I have a bubble of matter, of quark matter, which is rotating, and the typical length scale for the formation of, I mean, not to have a superluminal stuff at the surface is shorter than the confinement length. In my opinion, it should be string break. I mean, the formation of two bubbles, of more bubbles at the surface. So it will radiate. It would radiate or whatever you can call it. I mean, the strange light or whatever it is. It will radiate away this stuff. If it is larger, it is not the confinement that can keep.
Sorry, but there is no string in the confinement phase, so nothing to break. It's the confinement phase. We don't consider strings.
So can I say something?
Yeah.
Okay. Yeah. I think that the Massimo is always assuming some strict boundary to confine the system into some box. But that is, of course, the statement depending on how you impose a boundary. So, for example, in the case of the hermiticity condition, the wave function itself can actually go outside from the boundary, but nevertheless, the current is vanishing. That is actually a very mild boundary condition to keep a hermiticity. And so if you consider, for example, MIT bag model like boundary condition, and then, so I think that the maximum is completely right. And so that is essentially the small size system, right? And so that is the weakly coupled system like high temperature. But that is not necessarily the case. It really depends on the boundary condition corresponding to the physics situation of your interest.
Okay. Yeah. I think. I mean, I agree with what Kenji is saying. And I'm saying that. Let me say that it's not so general, in my opinion, to have this kind of boundary condition, because that assumes a confinement-like picture.
It seems that you may consider also heavy nuclei, heavy ions with high spins, and estimates the velocity on the boundary of that nuclei, and ask the similar questions about phase transitions with respect to the spin. It's all.
So note that for MIT boundary conditions, small systems are always deconfined because of asymptotic freedom. That's basic mechanism how you have nuclei inside nucleons inside small volumes, how you can define them. Yeah, so partons. So that's main point. So if you don't allow the particle to go outside, the system will be deconfined. And for example, on the lattice, there were many discussions how to work with small systems at early stages when lattice field theories were considered, how to extend the results to physical domains. So consider them sufficiently large so that the confinement is not imposed by the boundary. But maybe we can invent some boundary conditions which don't impose them, but I don't really know in the context of gluon dynamics, for example. I don't know what kind of boundary conditions which we should impose on gluon fields not to cause the confinement. So everything what we impose, they causes the confinement at finite volumes.
But I think that the most crucial the problem to putting such a strong the strict boundary condition is chirality breaking from the boundary. That is, if the particle is the bound inside of the finite system, then that direction, moving direction, must have must be changed as the boundary, which means that the chirality flip must occur at the surface. And so you have to actually make some compensation by introducing some cloud of the chirality source and so on. That is actually imposed in the traditional MIT bug model. But so if we are interested in the chiral physics, like the chiral vortical effect and so on, such kind of contamination should be avoided, right? I think that that is very important point.
So, Kazuya, do you want to add something? This is a question to you. Okay, so if no, let's see the next.
Okay, sorry. Sorry.
Yeah, yes.
Yeah, sorry. So as Kenji says, the main reason for our boundary condition is hermiticity of the Dirac Hamiltonian, and of course the boundary condition strongly affects the dynamics, especially near the boundary. But qualitatively, the inside of the system, for example, its transition except for the vicinity of the boundary should be expected to be irrelevant to the choice of the boundary condition. And of course, we don't know what is the best of course, there is no infinite potential well on the edge of the system, but we need to, we can choose some boundary system, so boundary condition, so that's the, for example, so that the system becomes rigidly rotating. Keep the shape of the system, something like that, and then you can choose the best of the best boundary condition as you are interested in.
Yeah, I just would like to mention that, for example, in Weil-Sim metals or Dirac-Sim metals, they have also at low temperature, okay, low energy, they have excitations which are similar to relativistic particles. It's an ungapped spectrum, topologically protected. And there you can also introduce boundary conditions. And those boundary conditions, they necessarily have to return your quasi-particle back to the medium. So sometimes it leads to chirality flip. So basically particle jumps from one Weil cone to another Weil cone just because of this reflection. So it's one should really adopt boundary conditions to the particular situation. I know, for example, for lattice gauge theory, people discussed at some small volumes. I think a person called Berg, as far as I remember, he studied how lattice gauge theory depends with the cold boundary conditions. So he considered the hot boundary conditions in hot medium inside some volume and cold outside. So it's, I mean, I'm talking right now about gluons. So it was more or less acceptable conditions with respect to thinking about the problem of expanding fireball in the cold vacuum. So it depends. One should really adapt conditions to the problem. So I totally agree with Kenji. So they can be violating chirality, can be preserving chirality, can be bug conditions, and we should think. But its system is dependent, yeah, on boundaries.
You may imagine the periodic boundary conditions as if you are in the inside of torus rotating system, and somehow you move or accelerate or some ring system as an accelerator. You really, with these boundary conditions periodic, you model such a geometry dynamics. If you like to have a realistic picture of this artificial condition of the periodic boundary conditions.
Yes. Okay. So the next one is also about the boundary. It's from Oleg to Kazuya. So is it possible to prove the absence of zero mode for any boundary conditions? And there is a comment from Kenji. So usually the zero mode has zero amplitude, so no contribution. But I don't know how general it is. So say if you have a strong B field, the wave function is localized. So effectively, some boundary condition is introduced, and still you have a Landau zero mode. So there may be some boundary condition you can cook up arbitrarily. This is also a question to Kazuya. Kazuya, if you want to add further comment or answer, please go ahead.
So
Yes.
before that, so let me point out that the Maxime also made a comment on this point.
Okay, yeah.
I think so.
Okay.
Yeah, I think that it's better
right
to
here.
Yeah. Thank you, Kenji. I didn't.
Yeah. Maxim also put the comment that there are zero modes at the boundary at the quantized values of the magnetic field, but this depends on the boundary conditions. And the discussion can be found in Maxim's paper. Yeah, zero modes and the rotation. Yes.
Yeah. So similarly to Maxine, I am the yeah, actually I wrote the similar paper about the some enhancement of the magnetic effect around the boundary. So which is nothing but the strong influence of the zero mode at the boundary.
Yes.
And and yeah, for any I don't know I don't know the exact proof for absence of the zero mode for any boundary condition. And that is the same as Kenji's answer.
I actually put in the questions, I mostly had in mind causality, so that without chemical potential at temperature, the just energy level is not crossing zero. So, and this is because of just boundary conditions. And I wonder how general is it?
Yeah, but of course, if you put some the system size scale, in my case, that is capital R, the radius size R, then of course you need that R should be appear in the physics, especially in the gap of the spectrum. So in that sense, this is a very general argument, I think.
Yeah, but and is it? I mean, how robust is a prediction as a result that really this R appears and energy remains at zero, as you showed, positive? So unless there is chemical potential and temperature. So how it depends? Does it depend on the type of boundary condition, or it is more robust? Or
yeah, I think robust.
It's not obvious. No, it's not obvious. So I must agree with Oleg. So this is very good point. So what we showed was actually the gap by the boundary effect. That is always bigger than the shift by the rotation, but this is very delicate. So we actually made a numerical comparison, and then we showed that one is bigger than the other, but this strongly depends on the boundary condition. So actually, that is there is no much difference. So this is very delicate comparison, and so I can imagine a situation that this inequality can be actually changed by the boundary effect.
I agree. But I'm just saying the absence of the zero mode.
Yeah, well, yeah, but the statement of the vacuum not changed by the rotation, that statement itself may not be robust. Of course, it is physically most reasonable statement.
Yeah,
but
for that point, I agree.
I would just like to add one comment about boundary conditions, as Kenji say and Sarata say. Just for example, you can take MIT boundary conditions, and you can take actually many of them, because as Kenji said, that if you have the fermion, which comes to the boundary, say normally, then gets reflected, then left particle becomes right particle, because spin stays in the same direction, but direction of momentum changed. But there is also the phase. So the wave function of outgoing wave can pick up the phase, global phase, like for example, theta. You just physically will have the same picture, but theta can be different. And it depends that the spectrum of eigenmodes at the boundary, those including, for example, zero modes, or the presence or absence of the zero modes in the boundary spectrum, depends on that theta. So in that sense, a boundary, we cannot say in advance, just without calculation, say that whether we have there about zero mode on the boundary or not. So for the bulk, probably maybe we can say something, but on the boundary, it depends on the theta, for example, this internal variable, which you have to compare. You have to know ingoing wave and outgoing wave together to compare to find it. So it's
I think that is a sort of a reservoir, right? Just like the chemical potential, right? Yeah. Of course, the chemical potential is along the temporal direction, but that is a sort of a spatial counterpart of the chemical potential. So in effect, you have some reservoir outside of the system. So this is not really the the vacuum nor empty. So the situation is very different.
Yes, totally agree. Yes.
When you break translation symmetry, every local inhomogeneous condensates breaks translation symmetry, and there is zero mode.
Okay.
If you break translation symmetry by some inhomogeneous condensates like
spontaneously. Here we talk about explicit breaking. So
Yeah.
we don't have any zero mode by definition.
Right.
Yeah, but this whether the causality constraint can directly show that there is no Bank zero mode, or the absence of a Bank zero mode depends on the boundary condition.
It's a good question. I have no idea. So maybe we don't.
I think that's the Oleg's original question.
Yeah, we don't know. So we don't see them indeed, because otherwise, yes, I agree with Kenji. It's just, for me, just some relation between Bessel functions, basically. Yeah, well, I mean, but maybe one can invent some specific boundary condition, maybe which gives it. There is no theorem on bulk modes.
Yes, yeah, this is a very nice question. Yes. And so maybe the answer so far is not solved. Okay, so the next one is from Adiba to Arata. Maybe there's a mistake. I think this one is to Kazuya or to Arata. Anyway, let's read this question. So isn't zero mode contribution becomes larger for smaller volumes? So in many boundary conditions, we neglect its zero momentum contribution so that chiral symmetry is restored for sufficiently small finite volume.
So sorry. Zero mode contributions.
Maybe Adiba, can you directly ask the question?
Yes. Wait, he said.
If we have time gap, I return to the boundary condition zero mode. Thing is, if you try to model real physics, not some artificial lattice and so on, and if you at last, at the results, you have real physical results, which can be compared to the continuum space, translation invariance, and so on, there is zero mode. If you somehow lose in your calculations, then how you restore it in the continuum limit?
So as I said previously, the boundary mode itself is very artificial, yeah? So if you want to look at the infinitely large system, then instead of the boundary condition, so you need to consider something, some interaction between the particle to keep the shape of the material. So this is very, I think, non-trivial to get the large system with some rotation.
Hello.
Yes.
Hello. Yeah. So it's Adiba, and my question is, yeah. So yes, yeah,
Please
discussion
go ahead.
about yes, thank you. The discussion about the zero mode and smaller volumes. So it's something that I studied in also various papers. That the zero mode contribution, of course, just becomes very dominant for smaller volumes, and that's why many of the boundary conditions doesn't take the contribution from the momentum equal to zero. And is there any way consistently we can include a zero mode such that it doesn't create such a volume effects? And perhaps we know that this symmetry breaking is something which is should be restored for sufficiently small volumes.
So are you talking about the zero temperature?
Yes, it could be zero temperature also, but as well as finite temperature too.
Okay, at zero temperature, there is no rotational effect. And
no, let's say if I don't consider the rotation, let's say.
No rotation.
Yeah. So
okay, in that case, maybe you have the scale quantity is just system size and the cutoff scale or the scale of the theory. And I think the amplitude of the how the zero mode contribute to the dynamics is depends on the ratio of these two scales.
Yes.
Yeah.
Okay. Yes, and since the questions has been discussions have been going on about MIT boundary conditions, something which I always studied, for example, Professor Chernodup's paper and all. So what I want to ask is, we studied this MIT boundary condition with this back constant and in the Lagrangian. And we know that the fermionic pressure from inside and the back constant has this associated pressure from outside. So that it's a static picture we have of the, for example, let's say of QGP. So is this something we know that the QGP is evolving? It's a dynamic system. It's something this boundary condition is not appropriate to describe the system. Is it like that?
It's a question to me?
Yeah, yes.
Yeah, okay, but
you can answer.
Of course, we divide system into two subparts, one external, other one internal, and we would like just to work with internal one. We just impose boundary conditions and study, for example, fermions inside, like in say, in some, you can consider sigma models or NGL models. You just say that, okay, come to the boundary and that gets reflected. In reality, of course, fermion which comes inside, it can actually experience so-called a kind of Andreev scattering. So it can go outside, it appear as meson, for example, and other fermion, anti-fermion will come again, or I mean, there are many different possibilities how to describe it, but it's more complication of the system. We right now address very simple idea. Just we would like to understand how QCD behaves under rotation. And of course, we know that we have those nice profiles, for example, which were discussed by our chairman, just how vorticity depends as we move outside from the center. But right now we say very simple question is, imagine that we have uniform situation when just everything, I mean, rotates uniformly. And at this end, we must put some boundary because uniform condition, uniform rotation at some distance will violate causality. So of course, if you consider real profile of rotation, I don't know, say ranking vortex in naive formulation, then we don't need boundary conditions at all because due to viscosity effects, the velocity will stop. We don't need neither MIT, nothing. But it's complicated because profile is non-trivial and it's a little bit more complicated to address. So in that case, it's a little bit more artificial to study those boundaries, but they induce some additional features which we don't want. And Kenji said, and I completely agree, we should adapt our boundary conditions to real situation, whether plasma or vial semi-metal, say, or something else. So that's so it's so we are
that's something, yeah, for input from experimental side. That's what you're saying.
In which case we can have a bound zero mode if we have a finite size system. For example, if we have a box, if I put a periodic boundary condition, do I have a zero mode?
Normally,
yes.
no. No,
But,
normally, no. Periodic. Okay,
No.
periodic.
Periodic we have it, but usually we exclude it, giving, like I said, the system chiral symmetry doesn't get restored effectively at small volumes.
Mm-hmm.
So
okay.
yeah, so that's what I asked. Initial question was, is there inconsistently we can treat zero mode such that we don't have to remove the possibility of zero mode or something?
You don't know really. I don't know. I don't know really. Yeah. Yes. Sorry.
So in which condition we can have a zero mode? I mean, without a rotation, just the finite size.
You can ask the same question for Casimir effect. It's simplest one, 1 + 1 dimensions. And there you can have zero modes, but you need to have a split calculation. For example, you have 2 points, you have 2 MIT boundary conditions at 2 different points for fermions in 1 + 1. It's basically, okay, simplest condition. Or to be correct, I mean, to be more or less good, say, consider just 3 + 1, but parallel boundary conditions. It's more or less physical. And then introduce MIT here and MIT there. And then you will have the difference between MIT phases, those thetas, which I mentioned. And then depending on the value of theta, you may have either zero mode or you don't have zero mode. It depends on the theta. Or you may have repulsion or attraction of those 2 boundaries. It depends on this theta angle. Or actually not on theta angle, but on difference between those theta angles at different boundaries. So, but as far as I understand, without explicit calculation, I don't know any theorem on existence or non-existence of the boundary modes. And for example, it's like for Casimir, we don't know whether it is attracting or repulsive. It's without explicit calculations, you don't know. So I don't know about any general theorem on that.
Okay. So for example, even if we have a photon in a finite sized box, photon is massless. In that case, still we don't have a
solution for every case. Maybe is the following: you always subtract boundary zero mode contributions. Sometimes they are zero themselves, sometimes not, but always by definition you subtract them. If any, you always subtract the contribution from zero modes. And this definition fulfills every case. Have you zero modes in modeling for finite volumes or have not? Anyway, you by definition subtract the contribution from zero modes. So neglect practically. In practical words, you do not consider zero modes by definition, because if somehow they are, you subtract contribution from zero modes.
But this may be okay if there is no rotation. If we start rotating, rotate the system, then the rotation would be able to see whether there is a zero mode.
Okay, so that depends very much on what you consider. For example, we can consider, say, zero modes which move along the cylinder. So in principle, they become zero only provided there is no momentum along the axis Z. So if they have some momentum, just then already there are no more zero modes. We call them zero modes because at some point they have no gap, but they really carry energy, and they must be, therefore, those zero modes must be counted. Otherwise, they will not take into account correctly. They will not show up as, you know, for example, angular momentum or energy of the system. They will be, you must take them into account because they are zero only at, I would say, volume zero phase space. Otherwise, they are non-zero. But you call them zero because they cross E = 0, you know, It's like zero modes along Witten strings, which are propagating, but we call them zero modes because at momentum zero, they take zero energy. Better to call them gapless modes, probably. It would be better notion. And then we will avoid all those interferences, logical interferences. So it's just gapless modes. Okay, call them like that. That's all.
Okay,
Yeah,
okay,
okay,
thank
maybe
you.
we, yes, okay, maybe
Thank
we
you, everyone.
continue. The next one is from Natalia to Arata about the renormalization, which is discussed in the summary. If you consider here small values of omega, you will come to the non-relativistic rotations and lose all the relativistic features, right?
Okay, the answer is no. Small omega is different from non-relativistic limit. Please imagine non-relativistic expansion of energy. Energy is given by the first term is mass m, and the second term is kinetic energy, p square over 2m. Mass is much larger than momentum. This is non-relativistic limit. But this momentum is completely different from the angular velocity. They are completely different concept. So we can take small omega limit and non-relativistic limit independently.
Okay, so let's go to the next one. It's from Oleg to Victor. The question is that to impose causality more precisely, isn't it possible to use the lattice being a sort of cylinder with say a circle, with cells remaining standard cubic one, like our constructed from bricks?
Yes, the answer is yes, it is possible. For periodic boundary condition, I think it is not possible, but for Dirichlet and Newman boundary condition, it is possible. The point is that I don't know what we can gain from this consideration. I'm afraid there will be no some specific, I don't know, everything will remain. I mean, all results will remain in this case.
Oh, what I think, Victor, we already discussed it shortly, right? So yeah. I thought that maybe here we have causality everywhere, and if in a sort of saturation everywhere near the edge. But if you have like you have just normal lattice, there are some either and if you impose say causality, I don't know, you need to impose it just in the corners, right?
Yes, yeah.
And there are regions where it is far from it, so just to also just we later we exchange mails with Denis. Maybe it's possible even to have a lattice like a wall. So this means that just this x squared plus y squared changes between two r squared. So, and then you may control this factor gamma square, right? Which
yes,
which
yes, this is it is not. I think for cylinder it is rather difficult to realize this lattice because you know that we have at small distance from the rotation axis, the lattice size is very small. But if you go to very large to larger, if you go to larger distances from rotation axis, in this case, your lattice spacing in perpendicular direction is much larger. And for this reason, I think cylindrical lattice is rather artificial. But if we consider, I would say, some so cylinder brought from one radius to another one, and then we control the lattice spacing in perpendicular direction is possible. Yes.
This is what then it's possible when velocity is small, right? And but the just the lattice the cells are still rectangular, so you don't need to implement the polar coordinates. So,
but in this case, if we just fix radius from one value to another one and consider our physics inside this slice, I would say, between two cylinders, in this case, it is possible to control finite lattice spacing effects. This is the point. It is, and probably it is possible to realize numerical simulation in such lattice.
In that case, of course, you would need the boundary conditions in outer, right? In
yes,
outer,
in outer and internal,
and in
yeah.
inner, right?
Yes.
I see.
But the point is that yes, it is possible to realize, but I don't think that a lot will be changed in this case.
I see.
Because what results we obtained? We obtained that critical temperature rises. I think it will rise in such coordinates also. What else? Coefficient will be different, definitely.
Yeah.
Because
I mean, you have gamma. You have gamma factor more changing in more narrow regions. So
yes, sure.
Right?
Yeah.
Thanks.
Okay, yes, that's all the questions that the organizers collected from the chat. So I think now we can go to, I don't know whether we still have some time. Maybe the organizers can have some comment on.
Yeah. I hear. Okay. So we took some extra time already, but if there are points, probably we can take, I mean, I don't know, maybe 10 minutes more. I guess it would be maximum.
Yes.
So.
Yes. Okay. Let's take about 10 minutes more for more discussions. And I see Maxim, you have a question or comment?
I have just one comment actually, because we're right now talking about clarifying boundary conditions, whether they're important or not. But we have a person here who can do that, who check at least for gluons. So it's Victor Braguda. You can ask him, okay, just take lattice, don't take any rotation. If already he did not do that, just don't take any rotation. Impose your boundary conditions and see how Polyakov loop depends on the volume of the systems with different boundary conditions. And that's why we'll understand how boundary affects the gluon vacuum, at least gluon vacuum without any rotation. So we'll see some kind of benchmark point, whether he sees the, say, the violation of this resymmetry. No, I mean, whether he sees the confinement due to asymptotic freedom or not. Clarify.
Yes, we actually did this at zero rotation because we wanted to check if it is possible to represent critical temperature for all boundary condition. And the answer is yes, it is possible to, but we have to take quite large volumes. So in order to, as compared to periodic boundary conditions, if we impose, for instance, directly on Newman boundary condition, it is possible to reproduce critical temperature, but the finite volume effects are sufficiently strong.
Well, just we wanted to understand how strong they are. So take, for example, directly boundary condition, or for example, I don't know, consider two physical conditions. Consider two of them and just take a small volume and see where asymptotic freedom sets in, where string is destroyed, or if it is destroyed or not. We would like to understand, because
we haven't checked this. So we didn't consider small volumes because we were interested in finite volume effects. So we had to consider rather large volumes. This is a point. And also we try to understand what is happening with the profile of Polyakov line, and it is seen that boundary conditions greatly influence the profile of Polyakov line, I mean the distribution. For instance, if periodic boundary conditions, they are uniform, I mean, without rotation, but in the case of Newman or Dirichlet boundary conditions, they are not uniform from the very beginning. Because, for instance, we have some region in the center, at the center of the, our lattice, which is rather uniform, I would say, and then there is a non-uniform region. I already noticed about this. This is due to the screening. So system have to screen these boundary conditions in order to reach physical, I would say, physical behavior, physical properties inside this volume.
Okay, thank you.
Xu-Guang.
Yes. Okay.
So can I say something?
Yeah, you can, please.
So yeah, because now I'm a co-host, I cannot raise my hand. So
I
raise my hand. Anyway, I want to actually pose a question. That is, so instead of putting any boundary condition, for example, we know from the hydrodynamics or kinetic theory that actually they introduce the vorticity in a local way. And then you don't have to impose the boundary condition. So now the problem is we actually make some trick to put the system into the rotating frame, and that is actually the source of all these problems, right? And so my question is there any way to put such a local vorticity in the quantum field theory? I mean, for example, as I showed you, the vortex, the quantum vortex is actually the well-defined object in that way, and we know from the superfluidity, if you have more and more vortex lattices, then eventually such the condensation of the vortex makes the angular momentum similar to the mechanical rotation. And in such a way, by choosing some winding number by some boundary, well, again, the boundary condition, but in a more well-defined way to control just the winding number. And then you can probably introduce the vortex 1, 2, 3, and many vortices. In such a way, maybe more controlled manipulation of the rotation could be possible. So what do you think? Some lattice experts, what do you think? Is it so? Arata, for example, did some vortex simulations of lattice, right? Isn't it possible? Or?
Well, can I answer?
Yes, please.
We were thinking when we were carrying out our study, we were thinking about this. And I would say that lattice geometry violates some, I mean, rotation symmetry. And for this reason, I'm afraid that putting, I wouldn't say about vortices, but about fixed momentum. So from statistical mechanical point of view, real variable is not angular velocity, but angular momentum. And it is okay if it is possible to put this angular momentum, fixed angular momentum, and put it as a chemical potential to the lattice. But this, if we consider rectangular lattice, I mean these blocks, cubic lattice, small lattice, and in this case, as far as I understand, rather difficult to realize this, because you should understand that something should rotate inside your and inside this lattice, and in this case, it is rather difficult to understand if it is possible to realize this rotating system in such cubic geometry. But for cylinder, in this case, I think it is possible, but we haven't tried to do this.
I see. Understand. Thank you very much.
And Oli, you want?
Yeah, if I can add, I think I had just a comment, maybe somehow similar to what just is discussed by Kenji and Victor. So in fact, why there is a problem with rotation, which is absent for magnetic field. And the point is, for magnetic field, the vector potential is growing in the same way as velocity for rotation. But the vector potential does not have physical meaning because of gauge invariance, and velocity is observable. So in some sense, in this sense, hydrodynamics is gauge theory without gauge invariance. From the other side, there is if taking periodic boundary condition, in some sense, because of a sort of monopole, the potential also started to be observable, and this is eliminated by the by the flux quantization. Maybe this is what Kenji has in mind. Maybe it's possible to consider in a similar way velocity and impose some sort of flux quantization, and maybe this can be similar to the consideration of a magnetic field. And this is just I don't know how this is practical, but and maybe what said Victor, maybe it's also has some similarity with that.
Yes, I agree. This is a very interesting idea, but unfortunately, right now I don't know how to realize it.
Yeah.
If you have an idea, I will be glad to realize. I mean,
yeah, just cylinder is. Okay.
Anyway, we can do realistic experiments. Take some device with a superfluid helium and identify what are the boundary conditions of that fluids at the boundaries. So these quantum vortices and superfluidity, everything can be experimentally realized. That's all.
Yes. Or maybe could this be done by introduce some special curved metric to incorporate the many vortices solution? I mean, if the global rotation can be introduced by using the frame transformation to introduce the curved metric, then is it possible to introduce the many vortex situation also into the metric?
You can introduce local rotation as a metric. It's really possible. It's ranking, for example, ranking vortex is the simplest example. You can do that really, and then transform to the lattice. So in principle, I don't see a really complication to that, apart from the fact that we will have some discretization effects. So you see lattice is rectangular and rotation is uniform. So some corners of that lattice will feel a little bit, so there will be some uncertainty. So one should really check that. But in principle, even local rotation can be written as some sort of metric, which according to Arata can be put and according to Victor can be simulated. So in principle, I think there should be no problem apart from the lattice artifacts because we want to make a cycle round. That's all, but okay, that's technical issue. There's no boundary needed.
Yes. Yeah, another thing from the simulation vector, it seems that the critical temperature of the deconfinement transition should increase with the rotation omega. From the talk of May, it seems from the holographic calculation, it's the opposite. Am I right?
Yes, it's like that. But my grandfather was serving a submarine. He said there should be 3 devices. Always critical devices should be 3. If one says one way, another one another way, and then we should need 3rd device to show the direction. So we need to have theoretical papers in this respect, and which proves, which says, I mean theoretical, I mean field theoretical papers and some specific confinement model to show, to discriminate between the two. So story is very interesting, and maybe it will depend on boundary condition, or doesn't depend on boundary condition, depend on velocity, we don't know. So maybe we'll have both up and down, we don't know. So it's, I have no opinion on that. I don't know if Kenji has any opinion.
Maybe the third study may come from the hadron resonance gas model. So you can introduce some notation on the hadron resonance gas model to see some blowing up behavior of the thermodynamics. And then maybe you can get some third answer from the third study.
Yeah, we should always have three, at least three. So if one points one, another one another, we have three which confirms more or less. Yeah.
Just from the physical intuition, how can we expect that how the rotation changes the deconfinement? For the Carroll's transition, it's quite simple because the rotation can polarize the angular momentum, so this favors the spin zero tendency. How can we see about the Polyakov loop?
Okay, as I told you, if you see the Polyakov loop, then the interpretation is quite subtle. But if you characterize the deconfinement by the blowing up behavior of some dynamics, like the entropy density or pressure, then it can be understood very straightforwardly. I mean, the energy is just shifted by omega times j, and so you can have such the more and more excitations, and so I would say that the deconfinement transition temperature should be pushed down by the rotation effect.
But
I'm just comparing the Mace result and the Victor's result. They are both about the Polyakov loop.
Can I interfere a little bit? I would like to say, usually people don't like to hear unfinished research, but I have right now some unfinished research which I have not finished by definition. So hope to finish it maybe in a week or two. So I address this question in scope of the one single theory, which I know very well, which describes confinement very well. It's a 2 + 1 dimensional compact U1. So I know that analytically you can do that in the calculations in low density limit, and it gives nice results. So I put the theory in the cylinder, I rotated it, and I right now would like to see what happens. I have not finished, but I see that, for example, if you have a monopole which stays at the center of the rotating universe of the cylinder, it does not feel rotation at all. So it's fine. That's already we see. But if you move to the boundary, then number of fermions get increased. But so that you could say that, okay, then you have more confinement to the boundary, less confinement in the center, so profile should be homogeneous in principle. So that's qualitatively that agrees what May says. On the other hand, the rotation can induce this BKT, Brzezinski-Kosterlitz-Taulis transition to deconfinement due to coupling of monopoles between anti-monopoles. And I don't know how it affects. So hopefully I will present results in 1 or 2 weeks. And it's only one model which I know in 2 + 1. But others models, I don't know how to, maybe like Kenji said, this hadron has resonance will be useful there. Could be, I never thought about that. So we don't know. We have to check. We have to think about a numerical, analytical model to address it. At the moment, we don't know.
Even with framework of the hadron resonance gas model, there is a way to compute the Polyakov loop excitation value from the spectrum of the vector mesons. And so that may give you some hint.
But I would like to warn about one thing about which I don't feel easy, but I don't know, I don't have really good argument. I know that, for example, if you consider effect of rotation on fermion, it appears as this vector as verbine. You get you get this curvature in the spin space. You get spin coupling. That's effect on direct spin on the spin of fermion. In the case of gluon, that does not happen. In the case of gluon, F mu comes with F mu. So we have F mu times F mu, and those indices, so inside F mu, you don't have J, you don't have metric tensor. So in that sense, it's different. It's kind of looks like more kind of geometric factor, but not spin factor, at least to me. So that's what I feel different. So I see difference between fermions and gluons in that sense, but we don't know without any correct fine calculation. We don't know at the moment. So, but there is
what about the strong coupling expansion on the lattice?
Oh, but it does not have rotational symmetry by definition. So it's
yeah, but you can introduce the metric and the Fermion.
Yeah. Yeah, you see, in strong coupling, that it is not related to continuum limit. So
yeah, of course, but that is a very the simplest model to describe confinement deconfinement.
Yes, the point is that I was trying to do this to calculate first correction, and turns out that it is in agreement with our results. So string tension increases as omega squared.
Okay. Oh, very interesting.
Nice.
But this is very preliminary, and it should be checked once again. I mean, with the action which was proposed, I mean, discretized action which was proposed by Professor Arata Yamamoto, and with this action, it is possible to show that string tension increases.
Very interesting. But I guess that the string tension must have their direction dependence, right? If you measure the string tension along the rotation axis.
Yes,
maybe
exactly. I was trying. The point is that I think that it is rather difficult to measure string tension in perpendicular direction. I tried to calculate it in direction along the rotation axis, but I chose the point which doesn't coincide with the axis of rotation, so it's at some distance. And in this case, first correction indeed increases the string tension.
Then isn't it possible to have the how to say some opposite effects on their confinement along and perpendicular to the rotation axis? Maybe
Well,
along
this
the,
I don't know. I don't know.
The confinement is disfavored, while along the transverse direction, maybe the confinement is more favored by the rotation.
I know the answer, but it's not good. The answer is the following: it depends on boundary condition, and
Yes.
on the lattice, it can be seen, but in different sense. Suppose you don't rotate at all. You just take the cylinder, or I don't know, some brick, long brick, and then if you put quark and anti-quark at large distances, and you say that your confinement boundary conditions, say, are magnetic, so I mean that magnetic field does not go outside, magnetic flux will be just squeezed inside, and you will get linear potential, which will be artificial, because you will get basically theory 1+1 dimensional theory with artificial confinement due to just topological reason. I mean, it's 1+1 theory. They have confinement because Coulomb is confinement in 1+1. Yeah. So, and string tension will be given just by coupling constant G squared divided by
Yes.
R squared.
Yes, in one-dimensional Coulomb is rising linearly.
Yes. But if you choose boundary conditions which are electric, then your magnetic field will go outside to the lowest minimum configuration. And in this 1+1 dimensional theory, you will get just the confinement. You will get static potential, nothing. I mean, you will get just flattening potential, because it's not really closed system. Your magnetic field will go outside and to the lowest. So it depends very much on boundary condition. We're coming again to this question.
For such anisotropic confinement, it seems that it will be non-potential forces. So maybe it will start to rotate the charges, so the rotation will go to angular momentum, something like that.
But I mean, just even without rotation, you have two different answers depending on boundary condition. It surely will be anisotropic, but you can have either confinement or not confinement. And maybe, by the way, could be also the difference between May and Victor. It also could be that they will in the detail in just what kind of boundaries they choose effectively. I don't know. So it's
If this boundary condition dependence is real, not artificial, it means that by boundary conditions we can control the behavior of the system to be in one phase or another. So it's a control parameter. Extra usual control parameter is temperature, angular momentum, velocity, or density. But now you say that by boundary conditions, we can control the state of system.
Yeah, but
so if this effect is not just numerical and artificial, but if it extrapolates to the realistic results, it means exactly that by boundary conditions, well-known, controllable way, you can control the state of the matter inside the device.
Yeah, sorry everyone. I think